this lesson, we will cover the Naïve Bayes Classifier. We will discuss what the Naïve Bayes Classifier is and how it works, the difference between categorical and continuous features, examples, how to avoid the zero probability problem, and the strengths and weaknesses of Naïve Bayes. A classification of problems can be modeled within the framework of Bayes' theorem. For example, given the handwritten digit classification, C is the class label and X is the image. A Bayes classifier computes the posterior probability of classifying an object based on Bayes' theorem. Notice here, we dropped the denominator term because it only depends on X, and X is constant across all the classes. In other words, it doesn't affect the classification decision, and we are interested in the classification, not the probability value itself. Again, the naive assumption in Naïve Bayes classifier is that features are conditionally independent given the class. So we don't need to compute complex joint probability distributions, and we can simply multiply the terms. For example, in a document classification task, if the class is sport, so words like touchdown and field goal are more likely to appear. So Naïve Bayes assumes that the occurrence of touchdown does not depend on the word field goal is present. It's only going to depend on the document being sport related. So this independence assumption significantly simplifies the computation. Here's an example to show the formula of computing the Naïve Bayes classifier on an example. This is an example from the Play Golf dataset. And in order to classify this example, I need to compute two probabilities. A probability of yes given X and a probability of no given X. And the probability of a class label given the example is going to be the product of individual probabilities of the attributes given the class label multiplied by the prior probability of the class label. And we learned how to compute these probabilities using counting from the dataset. Features in a Naïve Bayes classifier can be categorical or continuous. For categorical features, we estimate probabilities using frequency counts. In this example, I want to compute probability of feature outlook equals rainy given the class label yes. So there are 9 yeses, and out of those 9 yeses, there are 2 rainy with a yes, and this is how we end up with 2/9. To compute the probability of the example given the class, then we have to multiply these individual probabilities. When features are continuous, they are often modeled using a Gaussian normal distribution. So each class has a mean and standard deviation, and the probability of a feature given a class follows this Gaussian distribution, and then the overall probabilities will be the product of these individual feature probabilities. Now we are back to the Play Golf dataset, and our goal is to compute the class label for all of the examples in the dataset. So we better have a more of a systemic way to keep a track of the frequencies of different attributes given each class label, then compute the likelihoods so I can plug them into the formula. So here I have the probability of sunny given yes, I have the probability of sunny and the probability of yes, and I can compute the posterior probability of yes given sunny. Similarly, I compute the probability of no given sunny, then multiply them by the prior probability to get the classification. So here we have the full formula. So I computed the individual probabilities from these tables, and I ended up with these two values, the 0.00529 and the 0.02057. And you can see that I really don't need to compute the probability in the denominator, because I need only to look at the numerator to see that the probability of no given x is larger than the probability of yes given x. And this example is going to be classified as a no. In this example, Bayes computer, we are trying to predict the label Bayes computer based on a number of attributes. And maybe the storyline goes like the following. Someone is trying to predict whether a customer is going to buy a computer or not based on these attributes. And this information is very valuable because it's going to assess whether, for example, advertisements are working or not. So to get this information, we need to compute the probability of each attribute given the class, and then plug in the values to the formula and get the result. So we compute probability of age less than or equal 30 for yes, and then we compute it for no. Similarly, income, student status, and credit, the prior probabilities, we go and plug them inside the formula, and we end up with 0.028 for buying computer yes, and 0.007 for no, which means this example is going to be classified as a yes. One issue you may encounter is when your dataset has categorical values with no training examples for certain categories. So this problem is called the zero probability problem. For instance, suppose you have a dataset with 1,000 examples where income can be low, medium, and high, but for some reason, the training set does not contain any instance where income equals low. So when evaluating probabilities, the probability of income equals low will be zero, which is going to be problematic. To address this issue, we apply smoothing, and this technique is known as the Laplacian correction or Laplacian estimator. So essentially, we are going to add a value, typically 1, to each category. Then we're going to compensate the same amount in the denominator to maintain normalization, and then we compute our probabilities. In summary, the key idea is that just because the category doesn't appear in the dataset, it doesn't mean it's impossible to happen. So we need to be careful on how we compute these probabilities. Finally, we discuss the strengths and weaknesses of the naive Bayes classifiers. So these classifiers can perform comparably or maybe even better than decision trees, particularly in the high dimensional space. And a major advantage of the naive Bayes is that it supports incremental updates. So as the new data arrives, whether it's more spam email or more documents to classify, one can simply update the counts in the model without retraining from scratch. And on the weaknesses side of the naive Bayes classifier is its assumption that all the features are conditionally independent given the class label. And this assumption doesn't hold in many real-world scenarios. For example, in medical diagnosis, features such as the patient's age, family history, symptoms, and the condition are not independent of one another. So treating them as independent is going to be problematic. So that's why we are going to learn about more effective and complex models like the Bayesian belief networks. In summary, we covered the Bayes naive classifier, looked at a couple of examples, discussed weaknesses and strengths.